Okay. Well, welcome to the last technical talk of the conference, which just goes to show how much power I actually have as board chair to have the worst slot of the conference. Or maybe I'm just honest because I didn't use my influence to get a better slot. Anyway, as with the previous two presentations, I'm here to talk a little bit about monitoring these various fabrics and technologies. So I have a saying that it's always the network until it's not the network. So there's lots of different problems that get reported, and a lot of these times the first thought is it must be the network. So Lustre performance is slow from one of our clusters. Well, it must be the network. The NetApp is dropping and connections are dropping and coming back periodically. It must be the network. So anything that can possibly happen, somehow it must be the network. My chickens aren't laying this month. It must be the network. So just to mention, I have a couple things I'm going to talk about in this presentation. The IBMON process that Serge talked about is a process that I developed years ago and Jesse has improved, and it's being run at Los Alamos and Sandia. It uses all of some of the built-in tools that come with the package, and it pulls its information from the Perf Manager. So it uses Perf Manager, which is part of OpenSM that sits, in our case, on the master node. So that IBMON process is not putting anything on the wire. It's going to Perf Manager and pulling the information from there. And so that's where that reset's happening. But what I wanted to talk about today, mostly, is an approach that we have that's a little bit more holistic. So there's a lot of statistics that you can get on a very granular level, like they're doing with LDMS. There's a lot of different bits of data that you can gather. And so we are taking, one of our approaches is to take a more holistic approach. This diagram shows what a typical HPC, and I call it the I/O subsystem. So years ago, I started pushing the idea that the I/O subsystem basically starts at the HCA on the compute node and ends at the parallel file system, or the home and project space, or wherever it is that compute node needs to go. And so it's kind of gotten more diverse over time. So what you can see here is some of our clusters internally to the cluster are OmniPath. Some are InfiniBand. The I/O nodes, or the gateway nodes, that's an interchangeable term, they actually, most of them have three network technologies right now. So they have the internal cluster connection, which could be InfiniBand or OPA. They have a connection to our IB-SAN, which is where Lustre sits. And they have a connection to the Ethernet backbone, because that's where our home and project sits, and that's where licensed servers and other various things might be that the compute nodes ultimately need to talk to. So you can see that there's three different types of network technologies that we have to maintain, and we have to ensure that that's all functioning. I think the next slide is just kind of a drilled-in view of that. It just starts at the I/O node. And so you can see a little bit more detail as far as the amount of connectivity we have. So on the I/O nodes are basically managed as part of the cluster. That's something I've been trying to change but not been successful at yet. So it runs the same OS and image that the compute nodes run, slightly modified. We try to scale it down so it doesn't have all the compilers and MPIs and things like that. And in addition, it has a Linux tool for doing OSPF. So our Ethernet backbone uses OSPF to do its routing. So there's a tool on there, Quagga or Zebra, whatever term you want to use. The package is called Quagga now. And so basically the I/O node is a router and a media converter. In addition, now that we have Lustre, we have LNet routers running on these gateway nodes. So they're pretty much the linchpin between the users trying to get their job done and everything else that they need to get their job done. So that's the focus of this process called dead gateway detection. So this has been in development for a very long time. It's been on our systems for close to 8 years. Only in the last probably 3 or 4 has it been ubiquitous across all the clusters. And it's a fairly sophisticated piece of code, so there have been times when it's not behaved as correctly as it should. And so that always gives you a little black eye. But ultimately, it's pretty stable right now. And in fact, when we fielded our last set of clusters, they were virtually begging me to get this running on the new CTS1 clusters because we were having so many issues that they knew that it would help. So finally got some positive traction there. So what are the concept of this is to basically monitor the whole I/O subsystem, to proactively try to identify where faults are occurring so that you can remove that from the subsystem and allow the rest of the system to behave without this faulty piece in there. And to back up a little bit, the reason we really needed to do this is because when we used to have a failing I/O node, we found out because the users complained. So the user said, hey, my job's hung. And then you find out that it's trying to do a restart dump to the file system and it's using an I/O node that is dead in the water. So, so we wanted it to be proactive if possible. And we wanted to simulate the typical access patterns that users use. So make sure that the compute nodes can talk to the I/O nodes. Make sure that the compute nodes can ping the switch gateway. Are these connectivity, are these paths that they depend on, are they there? We wanted it to be stateful. It reports status. It allows administrators to control it and get easy access to the information that it's producing. So that was kind of the high-level concept. Some of the other criterias for it was, again, to define these points that it needed to test. You can define and choose which tests you want to run on any one cluster. You can set configurable thresholds on how many times that test needs to fail. Most of them have, like, it has to fail 3 times in a row, or we don't really consider it bad. Because obviously networks can be a little flaky, and you might at one moment not be able to talk to that specific element in the network, but it's a very temporary thing and transient, so you don't want to just react every time something doesn't work. We want it to be transparent to running jobs if possible, obviously. Run on all clusters, be driven by a configuration file so it's easy to tweak, and be part of the standard logging process. And really the ultimate goal is if we find an I/O node that's bad, we want to be able to take that I/O node out, let the rest of the compute cluster run, and then the operators, as they have time, because they have a lot going on, they can address that problem as they see fit, instead of rushing over there in a mad dash because there's issues. What this also allows for is an I/O node can go out on a Friday afternoon and nobody does anything about it until Monday morning, and that's okay, because that I/O node is not in the routes. It's basically not there. So a functional overview, it's written in Perl. I'm old school. I wrote it years ago, it's in Perl. Yes, it probably should be Python. I have an effort to get a student to just rewrite the whole thing because it also grew up kind of organically. Probably could be done better. I'm perfectly willing to say, let's just, like, good concept, let's rewrite it in something newer. I've yet to succeed in getting that done. Runs as a daemon on the master node of the cluster, reads a configuration file, discovers its world. What am I doing? How many I/O nodes do I have? How many compute nodes do I have? And then it goes into a while loop, and it just runs. And it runs through all its tests as driven by the config file, reports the health, and then goes to sleep for some configurable amount of time. Then it wakes back up and does it all over again. So fairly straightforward. What things does it test? It tests the functionality of the fabric NIC on the I/O nodes. So can I reach the fabric NIC, so IB or OPA, can I reach it? Some of these tests are run from the master. Some of them are run from a random number of compute nodes, driven by the percent of the cluster that you want to run. and then there's a max, right? Because I think we try to run 20% random. But if you have 1,000 nodes on your cluster, you probably don't want to run 20%. So we have all kinds of ways to configure this so that it doesn't take too long, but it does a fairly wide stretch of what it's testing. It tests the status of OSPF-D. So if OSPF-D dies, it can no longer route. I don't know if you're familiar with OSPF-D, but basically what it does is it turns the I/O node into a router that advertises to the Ethernet world, hey, if you want to get to this non-routable space back here, send me the packet, and I know how to get it to them. And so if that OSPF-D process stops functioning for some reason, then it can no longer route packets. So we check and make sure that that thing's working. We look at some various messages that we've identified, like IB transmit timeout. There's a couple of them that you might see in the syslog from an I/O node that is indicative of perhaps the NIC is failing or something on that node is failing. And any kind of message that we identify that we think is indicative of an unhealthy I/O node, we could add to that list. We check the connectivity of the LNet routers if you have LNet routers. Not all of our clusters have LNet routers. But if we do an L-control ping, and we make sure that we get something back. We're talking about adding more intelligence to make sure that what we get back is what we expect to get back. Right now, we just make sure it doesn't say I/O failed or whatever. When an LNet router doesn't respond, it just gives you some I can't talk to you message. If it's happy, it tells you this is my NID world. This is where I think I exist. So we could actually verify that that's correct. And then we do have some secondary IP space on some of our clusters that it will test that as well. So this is the same picture you saw earlier. The stars kind of try to graphically represent where our tests are running and what they're checking. One thing you might notice here is, I don't want to use this, I'll hit the wrong button. We have a set of Ethernet LNet routers out here. So we used to use Panasys, which is an Ethernet connected parallel file system. We switched to Lustre several years ago. But when we did, we had compute clusters that we didn't put IB interfaces in them. We didn't have an IB SAN really built yet. It was just starting. So we had a lot of clusters that were actually using IP over IB to get to the I/O node to get to an external Ethernet router, which then connected to Lustre. So we do have a set of Ethernet LNet routers out there. They're getting smaller because as we get rid of our old clusters, we may only have one left that actually uses these things now. But so that's where we're trying to test the various points in the I/O subsystem. And again, what we're trying to do is duplicate what the type of connectivity a user needs to have to get their work done and make sure it's going to behave. So again, we used to find out about these problems because a user would complain. In the last probably 4 years, and I should be more scientific and quantitative about this, but the number of times we've had to be told that there's a problem and we didn't know about it, it went to 0. I don't have numbers on how many times it found an I/O node and then pulled it out, but you know, the admins now, they realize that they can get the message that we got a bad I/O node, and they're like, yeah, okay, I'm busy, I'll do that tomorrow. And that's fine, because the way it works is when it sees that it takes some actions when it sees an I/O node is bad. And one of the things it does is it shuts down the fabric interface on that I/O node. And we have a process at LANL that builds our routes. And when it builds those routes, it tries to ping that interface. And if it's not there, it doesn't go into the routes. So, when an I/O node goes bad, we force that process to run on all the compute nodes, which takes that guy out of the routes. Now, these are Ethernet routes, right? But with Lustre, even though we're connected to an IB SAN, Lustre uses some IP over IB connectivity to make sure things are good as well. The other thing we do is we shut down the LNet router on that I/O node so that it's no longer acting. We didn't do that in the beginning, and we found that the server side thought that LNet router was just fine, but the client side saw that as no good. and it caused Lustre some unhappiness. So not that long ago, we added to the process of how do we shut down this node and make it, dead to the world. That's what we do. So there are some future tests we'd like to add. Like I said, is this the correct NID list? We've talked about launching tests from the I/O nodes themselves. There's other things that other commands, other data you might be able to pull that could go into this. So this is I kind of jumped the gun on my talk here, but this is the remediation that we do when we find a bad I/O node. We basically say this I/O node is dead, and it's out of the Ethernet routes. The LNet router is shut down. The OSPF-D daemon is shut down. So it literally, it's like it doesn't exist. And that's why you can wait a weekend. Sometimes we've waited longer than that because sometimes we miss the message that, oh, look at this. There's been an I/O node down for 2 weeks. But nobody notices because nobody's using it, so that's okay. And obviously it can handle multiple failures. We run fine-grained routing on our Lustre file system, for better or worse. And so our I/O nodes have to come in multipliers of the number of fine-grained routing groups we have. So 4 in one network, 8 in the other. So that means we may only have 2 I/O nodes for that one fine-grained routing group. So depending on which cluster, we have different levels set. We have an insanity threshold in case the dead gateway code has lost its mind and done something stupid, and it thinks that all the I/O nodes are, some large number of I/O nodes have all gone dead at the same time. If it hits that level, which is configurable in the config file, the dead gateway code says, whoa, I think I have lost my mind. I'm going to create a file called etc insane, and every time I wake up, if that file's still there, I'm just going to go back to sleep because I think there's something wrong with either me or the system, and it's big enough that I don't want to be messing with stuff. So that takes admin interaction because they have to go and see what the problem is and then remove that file in order for the dead gateway code to continue running. So there's signal handling in this thing. One of the issues is if it's sleeping for 45 minutes and an operator goes out there and fixes it, and you got 40 minutes before the tests run, and it takes a full, complete set of successful tests for that I/O node to then become active, you can have those 40 minutes when the I/O node got booted up and it's got a good fabric NIC, it's advertising OSPF-D, it's talking, its LNet router is up, but the compute nodes have not yet recognized it because we've modified those compute nodes to say this I/O node is dead to you, don't speak to it. So we added signaling so that you can basically shut down the process or wake it up as needed so that you can reduce the amount of time that you might bring a good I/O node back before it gets completely put back in the routes. So far, this is working pretty well. You can reload, there's a suspend, a reload. You can reload the config file. One of the cool things that allows you to do is change the debug level. So there's a level of debug in this guy that basically tells you everything he's doing. So if you think it's misbehaving, you can increase the debug level. It doesn't lose state. It just keeps running along, but it'll tell you everything it's doing. It's built as an RPM, runs on still RHEL 6, RHEL 6 and RHEL 7. It's on GitHub. There's source code. There's a test script, which is, I call it a test script. It's not actually a script. It's a series of tests that I run through every time I modify the code in any significant way to make sure that it's behaving as expected. And there's a spec file out there because the spec file has to know whether it's a RHEL 6 or RHEL 7, and then it builds the RPM correctly. I think I already mentioned it uses a randomly selected number of compute nodes for some of the tests, and has SSH timeouts. So if it tries to run these commands, like it's going to SSH to a compute node to test that the compute node can reach all this other stuff, if that compute node is dead, you don't want the whole process dying or stalling because of that. So there's SSH timeouts that say, hey, if you don't get a response in 10 seconds, just move on because you must have got a bad node. So that's the main tool. right? So to go back to how do you debug a problem in your fabric, it's hard to prove a negative, right? You don't think it's the network, but how do you say, we really don't think it's the network, can you Lustre guys please look at this now? Or we think it's the node, could the sysadmins please look at it? But you have to have some amount of data to try and point to somebody other than the network, right? So this is one tool we use. I'm going to talk about briefly two other tools. I don't know how much time I have.
15 minutes.
Oh, good. So I have two other tools that we use, which again they don't fully answer anything on their own. I don't think any of these tools do, but they give you more data, right? So we run performance baselines on all our tests. On all our clusters. And the way it looks is it uses the perf tests, IB read, write, bandwidth, latency stuff. And they are run via cron jobs that run alongside all the other user jobs. So we don't run them on DSTs, we could. But the idea is we want to get a running baseline of how our fabric is performing in the real world when everybody else is running, and Slurm's gonna run these jobs just the way it would run any other user job. And the MPI, so the reason MPI is used is just to get that Slurm and multi-node capability. So basically MPI goes out there, it discovers how many nodes it has, and then it basically does a system call to IB read write bandwidth. So it doesn't use MPI to run the test. It just uses MPI to discover what are the 64 nodes that I'm running on. And MPI runs with 1 rank per node. And then it says test. And so it runs every day. Every day runs, one day it's read bandwidth, and then it's send bandwidth, and then it's write latency. And so every day we get something. And this is a representation of, we are starting to use a tool called Grafana. I don't know, has anybody used it? Yeah, it's like a Splunk thing, but it's free, and I find it a little easier to use. We have somebody who's helping, push this technology. But what you can see here is, and it's kind of small, the lettering's kind of small, but at the top you can see there's a drop down for what test do you want to look at, and there's IB, send, read, write, bandwidth, and latency. So you pick the test, you pick the cluster, you pick the number of ranks, because we run at small numbers and we run at larger numbers of ranks. And there's a time frame in there. And you can get basically your speed. So this is an example from Kodiak, I believe, which is one of our, this is Kodiak. This is one of our newer IB systems. And so on one side, and the other thing I run what's called sequential, ring, and aggregated. So I do a sequential test where it's just unidirectional. Ring is bidirectional. And aggregate is if I have 16 nodes, I start one server and I have 15 clients and I hammer that one to make sure that in aggregate I'm getting what I should. So on the first side is the sequential, so it's unidirectional. And that turns out to be around 94 gigabits a second. It's reported in gigabytes, so that's what we'd expect, right? It's an EDR system, so that looks good. And then the other slide is an aggregate, so that's a 16 rank or 16 node process. So if you take 806 megabytes and multiply it by 15, you get 96. The aggregate one is a little funny because even though I use MPI barriers to say, go, go is still, the granularity is a little not always right. So there's 1 or 2 tests that probably get in there by themselves, and then there's 1 or 2 laggards. So it's sometimes a little higher than you might expect. But that's kind of cool because if somebody says, well, I was running on Kodiak for months, and then last week everything went to hell, it's the fabric. If I have these baseline tests, and they're only, it's 16 nodes, 64 nodes, it's random, I may not be hitting all the nodes that they're hitting, you can pretty much say from a general perspective, if these baseline tests haven't changed, there's not a fundamental problem on the fabric, right? So again, it's not a complete answer, but it helps. And then this is just an example of a latency test. So these run on our OPA clusters as well. Right now they are running verbs, which is kind of okay because OPA clusters use, my understanding is verbs with their LNet. The LND that's used is still a verbs, IB LND. So it's not completely wrong. I'd like to get some very fundamental PSM tests that don't have MPI as a layer, because if you misconfigure MPI, that could be affecting the results you're getting when I really just want to know, is PSM working? And so I'm still kind of pursuing that. So that's one tool. The other one is, as we were talking earlier, when you see problems on your fabric, and maybe you can, and we do, you track how many packets left that port and how many packets entered some other port. If you don't know what the route was between node A and node B, then all those intermediate ports on the switch, you may not know which port it took at any one time, which is, we were talking about the problems of that. So I have a set of scripts which used to be kind of kludgy, and I would just run them as I could. And I've cleaned them up because the consultants want to be able to run them. And so basically what I do is, in this case, and I plan on adding the ability to go from what's my compute node allocation to all my IO nodes. At this time, it's just compute to compute. And again, this goes back to if your user is complaining and they're in the middle of a calculation, they're not dumping a restart file. The IO nodes are probably not in the mix. But if they say their time steps are taking longer, and all I do during my time steps is maybe some all-to-alls, which are not only some all-to-alls, they're painful. But what I've done is you can take a Slurm job ID and send it into this script, which goes out and grabs the routes between all of those nodes and basically gives you and you end up with a GNU plot of all the switch ports that are used in that job allocation. So we really don't care about, the HCA port. So the only thing that's graphed here are the ports that are used when you look at a route map for a certain job. Again, doesn't tell you anything in and of itself, but in the past we've known that, well, we think, spine card 209, we think maybe it's starting to look funny or something. If somebody's job is acting funny and they got a bunch of routes that are going through that spine card, well, maybe that is what's going on, right? So again, these kind of tools, they only really help in aggregate, right? Because you can look at them all and hopefully come up with something. So basically, like I said, I have some desires to make this a little bit better. I think I need to wrap it in a set UID script because the consultants don't have root. And I've lived so long with root, I just don't know how I'd live without it. So sometimes I don't understand, what do you mean it doesn't work? So I may need to make it even a little smarter. And for the IB one, I finally got a patch, yay, into IB traceroute. I modified my own version a long time ago and decided if I was going to talk about this, I should probably push that patch into like the real world. And so it's out there now. One thing I had to do was IB traceroute out of the box. You give it 2 lids and it gives you a route. Well, if I have a 128 node job, that's basically an n-squared problem, and it takes forever to call IB traceroute 128 squared times. So I submitted a patch to be able to send it a file. So you're not launching and tearing down all those times. And it greatly reduced the amount of time it takes to get the routes out. So that's all out there. This is all on GitHub as well. And just this week, while I was in the conference, sorry, it now works for OPA. So I was not aware of OPA's got a lot of commands. They really do. And I was not aware of how to dump the routes on an OPA fabric. And I found out earlier this week how to do that, and so I added the capability to the to the script. So basically there's two scripts involved. One grabs all the routes and pulls out all the switch port stuff and does a sort and a unique and a count and all this stuff. And then there's another script that kind of modifies the X-tick on a GNU plot command so you can get those somewhat human readable X values. So this is all out on GitHub as well. And the reason why I think some people will say, well, routes can change. They rarely change. Unless you have like some major failure on your spines, the routes are pretty stable. So if you do this in a close proximity in time to when the job was running, you can even do it while the job's running, which I've done, then you know you're going to get a pretty clear picture of the routes that job is using at that time. So again, it's dangerous sometimes to give people information like this because they can look at those spikes and go, oh my God, or they can say it's not balanced, this looks terrible. And that's not necessarily true. So you have to be careful what you can glean from this information. But I feel like the more tools you have in your toolbox, the more likely you are to find the answer, and you're more trustworthy when you go to the big meeting where everybody's talking about why they think the network's broke, and you can say, well, my baseline tests haven't changed, the routes don't look that bad, IBMON isn't showing anything, we don't think it's the network. But if you just go in there and say it's not the network and you don't have any data, you're not going to get any traction. So that's my story, and that's it. So it's, like I said, it's out on GitHub. I work at the laboratory, so we have my license files on GitHub just say something like, yeah, we built this, but it came from a government agency and we don't care, and here's this number that proves we don't care. It doesn't really say it's GNU, but you guys can use it. Any questions?
Yeah, thanks, nice tools. I would suggest in terms of the IB traceroute to modify, I think there's just a flag, or you have to modify the OpenSM a little bit to dump you the routing information every time, and then use that in terms, because it's much easier to parse the routing file and then correlate it with the job information. I have a bunch of Python scripts which do that.
I've looked at that, and this is just my own failing, I guess. I've looked at those routing maps that get dumped from OpenSM, and I can't make heads or tails out of them. Now, I'm sure there's probably documentation somewhere that tells you, and I know there's probably already tools out there somewhere that tell you what they say. But as usual, I mean, there's lots of tools out there, and if you don't know exactly where that tool is when you need it, you basically build your own. Yep. And so I had always used IB traceroute because it's human readable. It says lid this, port that, and if you use your IB node name map, it even gives you the actual human readable switch name. So I found that easier to start with, but you're right. This could be done possibly easier, depending on what you're looking for. It could be done other ways. You're right.
We should talk about that. Maybe we can improve the stuff for both sides.
Yeah, well, that could be. Yeah.
And the other thing, your IB tools which run in the background on the nodes every day.
Right.
Is that only nodes which are free at the time?
You mean the performance tests?
Yeah.
Well, my cron jobs just submit a Slurm job.
Okay, so
and then Slurm gives me whatever nodes as Slurm decides what it wants to do. Okay. So, and again, the idea was let's try to replicate the user's world and see what we get, which was the idea with the dead gateway code as well. Let's replicate the types of network traffic that users experience
So
and use that as our guideline.
okay. So you don't have like a fixed interval. You basically, when something gets free, then
Exactly, and I
Sometimes
run
it's-
with like HPC dev as my priority, which is low. So sometimes
Okay.
these things can sit all day before
Yep.
they actually launch, because I'm like low on the totem pole. But I get out there just like any other user,
Okay.
but with a little lower priority. But I do have smaller, I tend to run, these don't run very long. So if you put your wall clock time low enough, which I've done, then you get in a little faster, because Slurm is real smart and it says, hey, this thing's only going to run for 10 minutes, so let's just get it in there. So, yeah, I just let Slurm do its thing.
okay, nice, thanks.
Yep. Yeah?
You mentioned about, I think, an HCA failing.
Mm-hmm.
How do you detect that?
Well, there's lots of different ways. Ports can fail and HCAs can fail, obviously. Normally what we see is in the IB world, you see symbol errors, or you might see the link width drop. In the OPA world, you'll see link quality indicator go down, stuff like that. And sometimes you can just, we have, our operators have a whole, they don't really have to come to us anymore. They have a series of things they try. They might try just reseating the cable, or they, reboot the node, or, they try different things, and then sometimes it comes back, and then, of course, if it happens again the next day, that's indicative usually that either the cable's failing, or maybe the HCA is failing, or the motherboard. Sometimes the motherboard's failing and you got a bad PCI slot. So it's not the card, but the card is manifesting the error. Yeah. Anything else? Okay, so I believe that we are now on a break. Is that correct?
That's correct.
And after the break,